So our next speaker is Bert Vries, professor from Technical University of Eindhoven, and I was a student. I am a student of Bert Vries, so I did my PhD with him, and yeah, so the journey started about 4 years ago, more than 4 years ago, and I joined the lab, and Bert was very passionate about Julia. I never touched Julia before, so I joined the lab. And yeah, I started to use this language because that was the only language that we use in our lab. I learned it. So in the beginning, I wrote a package, rocket.jl, and I submitted it to JuliaCon, to my first JuliaCon. And it was in Portugal, I guess. Well, it's supposed to be in Portugal. And I couldn't go because of the corona. So it was first conference, I couldn't go. OK, can happen. Next year also was online. Next year was online, okay, couldn't go. Then last year it was in US. And okay, I knew that I need to apply for a visa, so I applied really in advance. I applied like 8 months before, and I couldn't get the visa, so I couldn't go. So this year, we do it here in Eindhoven, so I don't have to go anywhere with Bert Vries. So Bert Vries, it's your stage. You are going to talk about the research that we do in our lab. Natural artificial intelligence. It's really a great talk. So listen carefully and prepare your questions. Round of applause.
Yeah, thank you very much. Thank you, Dimitri, for the introduction. Thank you for coming out. It's 9 a.m., it's raining, so you could have just opened your browser, so I really appreciate you being here. My enthusiasm for Julia is indeed about 10 years old, but it was really instigated by Joris Kraak, who is working for Julia Hub now. We were colleagues at the time, and working with MATLAB, and Joris said, forget MATLAB, even Julia 0.3 is better than MATLAB. So we've been we started to work on Julia, and yeah, haven't quit since then. I'm going to contrast what I'm going to talk about, natural artificial intelligence, with the current AI, well, I wouldn't say hype, but the current state of AI, which is generative AI. Generative AI, ChatGPT, I love it too. Everybody uses it. It's fantastic aid in productivity. But there are some shortcomings. And for instance, there's no real-time learning in ChatGPT, right? And in generative AI in general, you can't just go out with ChatGPT and ask it to learn how to ride a bike. It's just not designed for that. It tends to hallucinate. It's very hard to check if what the answer you get from ChatGPT is actually correct, right? It's very resource hungry. Obviously, not just in data, also in computing power, in number of people that are involved. And it's a kind of a black box. If you get an answer, it has troubles explaining itself. And these shortcomings contrast quite heavily with how we behave, how we learn, right? If I learn how to ride a bike, I do that in real time. I don't read 1,000 books on learning how to ride a bike. I just go out and ride my bike, and I fall, and I learn on the fly by trial and error. Our hallucinations, at least when we open our eyes and our ears, are corrected in real time by sensory imprints, right? We hallucinate in our dreams, but when we open our eyes and our sensors are open, we get a real-time correction. The whole brain consumes about 20 watts. There is a computer, the biggest supercomputer in the world, I think is in Tennessee, and it does about the same computation as the brain, but it consumes 40 megawatts, so that's 1 million times more computations for about, or 1 million times more power consumption for about the same amount of computation. The cortex, where the real stuff is happening, consumes only 4 watts. That's the power of a bicycle light. And we tend to be able to explain our reasoning, right? We tend to be able, if you ask me, okay, why did you say that? Well, I usually have I can give a reason for that. So that's the kind of learning that we're interested in, at least in our lab. And what we try to do in our lab is to find out how is the brain able to do this? And then use that for agents like ourselves that go out in the world. robots, drones, and other agents that go out in the world and learn in real time on a power budget because they're usually battery driven, and that are explainable. And so then we need to learn how does the brain do this, right? And so we need to go to the physics because the brain is just a physical organ. It follows the laws of physics. So I'm going to do a little bit of physics. And so the question is, it's a very basic question, right? If I have a ball in the left upper corner, black ball, and I throw it at T0, and it ends up in T1 at the spot on the right. And let's say it takes the black path, and then I can ask you the question, why does it take the black path? Why doesn't it take the red path? And you will likely say, well, that's just Newton's law. I can compute that. And that's entirely correct, right? You can compute that path with Newton's law. It just turns out there is a sort of a higher principle in physics from which you can derive Newton's law. Newton's law is perhaps not the most fundamental thing we can say about that path. And this is Lagrangian mechanics, and in particular, the principle of least action. And the principle of least action says, in nature, energy differences of any kind are minimized as fast as possible. So if I, for this ball, if I write down an energy difference, in particular, the difference between the kinetic energy and the potential energy, right here, and I minimize this over time by differentiating, then I actually derive Newton's law. Right? This function, this energy difference is called a Lagrangian. And this is true for bigger things in the world, right? Big things that move around. And if we have very small things, we can also write down a Lagrangian for small things, differentiate and get the equations of motion of small things, or Schrodinger's wave equation. For charged particles, we can write down a Lagrangian, the difference between electrical and magnetic energy, minimize it over time, differentiate, and we get Maxwell's equations, and so forth. And physicists like to put on a mug the Lagrangian of the world, right? And they say, well, this is the Lagrangian, the standard model of physics. All that happens in the world is, well, this Lagrangian is composed of energy differences of any kinds, and this is minimized in least time, and that's what's happening, right? So then the question is, hey, well, the brain is a physical organ. It should follow the laws of physics. We have movements, information movement in the brain, thoughts, reasoning. Is there a Lagrangian for that? Can we describe how we think, how we learn, our behavior by minimizing energy differences? And so Carl Friston says, yes, we can. And Carl Friston is a very famous neuroscientist in London. And he wrote down the Lagrangian. And this is the Lagrangian. And this Lagrangian is a function of probability distributions over states. So what does this mean, right? This, on the right, this picture is from a very interesting article in Wired magazine that is really fun to read. What does it mean? What does the brain really do, minimizing this function? This function is called a variational free energy. Well, it means that the brain is also a generative model. It builds a model with which it tries to predict our sensory imprint, right? And it, by receiving, and then you get prediction errors, and from these prediction errors it learns to build this model and change it over time as the world changes. To see that, or to illustrate that, here is a picture. It's called The Gardener by an Italian painter in the 16th century. And what do you see? Well, you see a vegetable bowl, right? And if I turn it upside down, the first thing you see is probably a gardener's face. Why don't you first see an upside down vegetable bowl? Well, when we go around in the world, we see a lot of straight up faces, a lot of straight up vegetable bowls. So we build a model to predict straight up faces and straight up vegetable bowls with higher probability than upside down faces. The data, our sensorium, is consistent with both, with an upside-down face on the left-hand side. This is also an upside-down face as well as a straight-up vegetable bowl. But our expectations are much higher for straight-up objects. So our perception is this Bayesian fusion of these two things, and so that's why you get to see a straight-up vegetable and a straight-up face. It's only possible because we actually have a generative model of the world in our brain. From here on, it's just going to be mathematics, right? I want to talk a little bit about this about this variational free energy functional, a little bit, and the actual math doesn't really matter. But this variational free energy functional, this Lagrangian, is the only thing that's going on. Minimizing this Lagrangian is the only thing. It accounts for learning, perception, our behavior, attention mechanisms, everything. In the machine learning community, it's also known as a negative elbow, which means evidence lower bound on Bayesian evidence. It's a way, minimizing free energy is a way of doing Bayesian inference in a computationally effective way. It turns out that I can decompose this free energy functional into two terms. On the one hand, of course, minimizing free energy leads to maximizing accuracy. We want to get accurate predictions. We want to predict the world well, because if I cannot predict the world, then I cannot cross the street. Right? I will get driven over by a car. On the other hand, we have a limited computational budget. Right? We have limited time to make our computations. We have limited computational resources, limited sugar. We have just 4 watts. And limited data. So, but minimizing free energy also takes that into account. It doesn't just keep building bigger and bigger models. It actually trades off. It wants to get the best accuracy for a very limited budget. It will not learn, it will not go on to do more accuracy than you need to solve your problems, because it will conserve the energy. We may need the energy in our brain to solve other problems. On the other hand, there is a second decomposition at the bottom that shows that brains learn at the same time a problem representation and a solution. Both the problem representation learning and learning the solutions are just implicit in minimizing variational free energy. The problem representation learning would be learning the model, and doing the inference would be the posterior, and that's going to be your solution. It means that a brain also, we will never learn, we weigh off problem representations and solution. It's useless to have a perfect problem representation that I cannot solve. It's also useless to have a poor problem representation and solving it exactly. I need to have an adequate problem representation and solve it adequately. And we will never spend energy on formulating problems more accurately than we need and solving problems more accurately than we need. There's always this force in conserving our power and just spending just enough computation that we need. That's why the brain is 1,000,000 times cheaper than regular computers. Now, this is not just some oddball idea. This free energy principle, as Carl Friston calls it, is actually, it follows from straight physics. It follows just from the same approach to statistical physics as physicists have done for centuries, and with the right assumptions. Right? There's an assumption that Friston takes is, he says, well, you exist as a thing, you are separated from the world, and what kind of processes must there be in place inside you in order to preserve that, right? Because once you are dead, you get reabsorbed into nature, but being alive means we resist that reabsorption. What kind of processes must be in place there? The free energy principle is a straight consequence of that question. Right, and these ideas, Fritz is also not the first one to come up with these ideas. In the control theory, people have proven that in order to make a good controller, you must build a model. And he also hypothesized then that the living brain must be a generative model. And this goes 50 years back. There are other papers from information theory, and even recently from in vitro measurements, just the biology in vitro networks of rat cortical neurons that show very strong support that brains minimize variational free energy. That's what's going on. From whatever view you look at it, whether you look at it from the physics view or from an information processing view or even biological in vitro, free energy minimization is the information processing that goes on in the brain. That makes it very clear for us, let's say an engineering lab here at the university in Eindhoven, of what our agenda is. If we know the math and the physics of what goes on in the brain, well, we want to get that math in on our Raspberry Pi or on our iPhone and send that iPhone in the world and say, now learn purposeful behavior, just like we do. Because our brain, by minimizing free energy, is an algorithm designer, right? We go out and learn to recognize speech. We go out and learn object recognition and navigation. There isn't an engineer, it just follows from apparently just by minimizing variational free energy, we design all these algorithms, we recognize problems, represent them, and solve them in the field, and learn how to ride a bike just by trying and learning, right? So that's the kind of intelligence that I want in my iPhone, and we call that natural AI because it's really based on the physics of natural systems. So in the end, the computations that we need to do in order to build these natural AI agents is variational free energy minimization or variational base, because it's the same thing as Bayesian inference, as they would call it in probabilistic modeling. Are there packages or toolboxes around that do Bayesian inference? Yeah, there's lots of them, right? Even in the Julia community, there's Turing. There will be a talk later today, I saw, on more advances in Turing. There's Gen, and they're also in other ecosystems like Python and Ruby for that matter. There's also toolboxes, but for Bayesian inference. But we want something special, right? Our toolbox must be low power. We want to go out in the field, battery driven, real time. If I learn how to ride a bike and I'm falling, I can't take a minute to think about what's action to take. It has to, I'm in a real time loop with the environment. I need to still get performance. Right? I must be doing variational free energy minimization in a productive way. Of course, it must be user-friendly to code this all up, because who's going to code these Lagrangians and do all this minimization in real time? We want to have big models, right? So all these desiderata that we need for natural AI systems to go out in the world, that's not currently the focus of the toolboxes that are out there. And it hasn't been over the last 10 years. So about 10 years ago then, I got a chance to start a lab at the university here. And these are a host of PhD students and former PhD students that have worked on a toolbox in Julia to do just what I talked about, to do variational free energy minimization, but to do it fast, efficiently, to make it user-friendly, all the things that we want to support natural AI. And so these guys have written lots of dissertations because this is hard stuff. There's a lot of math and physics behind it. Also, the coding is certainly not simple. And in the end, we have built an ecosystem in Julia. The ecosystem is called RxInfer. And RxInfer consists of a set of packages. And the most important packages, I'm just going to project them on this picture here. So from the user's perspective, if you're an engineer and you want to build an agent that goes out in the world and learns how to ride a bike, we have a language for that, GraphPPL. And GraphPPL is a very high-level language, and we really took advantage of meta-programming in Julia. Wouter Nuiten actually has done a lot of work on this recently, and later today he will also have a presentation on this. It's very easy to build a model. You just write Julia code, and if you have random variables, you use this very common thing of a tilde to say, well, theta is actually a random variable drawn from a beta distribution, and so forth, and you just write your model. Technically, that's all you need to do. Then you just put that model in our agent, and you just tell the agent, now go out and you communicate with your environment, you have sensors and actuators, and all you do is minimize your variational free energy. And that's what we want to automate, because that's really very hard to write out in math and in code. And that's what the toolbox is about. We support that with two toolboxes. Reactive MP, reactive message passing, I will get back to that, is a package that will do the actual variational free energy minimization in the agent. And RX environments is a package that in which you can simulate an environment. Now, why does it say RX environment and RX infer? Because this is reactively coded. These are agents that go out in the world and spontaneously minimize their free energy while they are communicating with the world. Just like for us, there isn't an engineer that writes a program for our brain. We're just doing spontaneous free energy minimization depending on our interactions with the world. So this needs to be coded in a reactive way, and so there is a package underneath Rocket that Dimitri designed a few years ago that both reactive MP and RX environments use. And these are the 4 most important packages that constitute the RX Infer framework. As a designer, you really only need to worry about doing your model. This reactive MP and RX environment is just basically a system simulation that minimizes its free energy. So RX Infer is hosted at GitHub. It's open source at the GitHub organization Reactive Base. And I want to talk a little bit now about what's under the hood of RX Infer, because there is a specific way in how we minimize free energy that makes it actually effective. Here's an animation of what's going on. It's a graph, and in this graph, messages are being sent to other nodes. I want to talk a little bit about that because it shows, because it's no accident that the brain is a graph of neurons, and these neurons send messages to other neurons. So let's assume that I have a function. So this would be my Lagrangian function, but let's assume it's just a probability distribution, f of 6, or is it 7 variables x. And let's assume that not everything depends directly on everything. So there is a factorization possible. This function f, this joint probability distribution, can be written as f1 of x1 times fb of x2, fc of x1, x2, x3, and so forth. So it's a simplification. I can represent that simplification by a graph where these functions fa, fb, fc are nodes, and the edges represent the variables, and a variable or an edge connects to a node if the variable on that edge is an argument of that function. So fc connects to x1, x2, x3. This graph just represents the factorization, nothing else. Now, the most common operation in Bayesian inference and also in variational free energy minimization is marginalization, which means I'm interested in the probability distribution over x3 and not over all the others. I need to sum over all the probabilities of all the other variables. In this case, I would need to sum over x1, x2, x4 until x7. So how many terms do I have in this sum if each variable x has 10 values? Well, it would be 10 times 10 times 10, 1,000,000 terms. But because of this factorization, I can use the distributive law. And some of these functions, like fc, doesn't depend on x4 and x5, so I can move that function basically over the summation sign. We're going to represent now a sum of products by a product of sums. How many additions do I have here? Well, 100, 100, 100. This thing is just a few hundred additions. It computes exactly the same thing. And it's only possible because the graph is sparse, because not every variable depends directly on every other variable. Now, just think of the brain. The brain has 100 billion neurons. And each neuron is, on average, connected to about 1,000 other neurons out of 100 billion neurons. So this is a hugely sparse graph, right? I mean, you cannot almost not imagine a sparser graph than a brain. If the brain wouldn't, or it turns out, let me just say one more thing. These auxiliary, these intermediate products in red, in blue, in green, you can think of that as messages on the graph. Everything that is in red is computed based on FA, FB, FC, which is just the left part of the graph. And this whole computation is just a matter of message passing on the graph. So in the case of a very, very sparse graph like a brain, it would be insane to not use message passing to do variational free energy minimization. Because even if a small graph like this, we go down from a sum of 1,000,000 terms to a few hundred. Now there's more in message passing, and particularly in Bayesian message passing, what we do. Let's say we have a graph here, and I want to minimize my variational free energy. I want to do my reasoning on this graph. So all these nodes pass messages to each other. We implement this in a reactive way. These nodes are just autonomous systems. They're just by themselves trying to minimize their own free energy by listening to messages from the environment. And each of these nodes is doing the same thing, minimizing its free energy. Which means, yeah, it will send out a message only if it expects that the accuracy increment offsets the investment in computation. Each of these nodes are also energy preserving. Yes, they want to maximize accuracy, but only as much as needed, right? So in any particular time, maybe you just have these amount of messages. And this also goes on in the brain. The brain is a huge model, but it's extremely sparse. And even on this sparse model, at any time, very little computation is going on. Only computation is going on where we have large prediction errors. So in the end, not all of this is working currently in ArcSinfer yet. But in the end, my speculation is that if we want low power, scalable computations for AI, it's going to be because of the fact that we do Bayesian computations rather than in spite of. The thing about Bayesian computations and Bayesian approach to AI is people agree that on theory it's the right thing to do. But in practice they say, well, but we can't do it because it doesn't scale well. So what we're here to say is that we think that it is because of Bayesian inference that in the long run we can actually do AI computations that are accurate, real-time, and low power and scale. Now, does it work? And it does already, right? ArcGIS works. So here is a warehouse navigation problem. There are agents. These agents start in the blue star, and they have to carry a package to the red stars. And then there are the obstacles. The blue bars are fixed, and then there are obstacles that just move around. The agent doesn't know about them. So the agent particularly doesn't know about the moving obstacles. So it will just plan by inference where to go, and hey, if it moves an obstacle, it's going to avoid it, because we have built in the model that colliding with obstacles has very high free energy, and the agent is going to minimize its free energy. We will never code what the agent will do. It depends on what he encounters in the world. On the right-hand side is a drone, and this drone needs to follow a moving red star. What we do here is in real time, as you see in the bars below, we just change the world in real time. We change the gravity, the engine power, almost everything that we can change, we change. And the agent keeps following the dot, no matter what. There's real-time adaptation going on here. We didn't pre-program an algorithm. We just said, this is your model. These are the constraints that you have adhered to. Now go out in the world and minimize your free energy. And it works for warehouse navigation, drone control, and we have lots of other applications. The real interesting thing here is if you look at the code that a user has to write. Right? What the user writes is basically write a model in GraphPPL, and then at the last line you see infer, do variational free energy minimization. This model is 15 lines. It's not so hard. You just write what are your variables in your system, and what are the relations, probabilistic relations between these variables. And this will solve the warehouse navigation problem. We did not write an algorithm to do warehouse navigation. We just say, well, there is some agent dynamics on the top line or the third line. We put in some probabilities for collision, and we set these probabilities very low. We put some constraints on speed, and we say some probabilities on start and endpoint position, and then we just say, now go out in the world, you will receive inputs, and minimize your free energy. And it will do warehouse navigation, and it will change on the spot if the world behaves in unexpected ways. So we're very excited about this, because this shows that you can actually go in one page of code or half a page of code, you can actually set up a model. It's not so hard actually to specify a model. Put it in a drone and just let the drone learn its own behavior. So we started a spin-out from my lab about a year ago, and these are the guys that are involved. So you recognize Albert on the left and Dimitri. And yeah, our goal is to basically a bit what how Julia started. Julia started with this idea. There is this two-language problem. People would say you cannot have the user-friendliness of MATLAB and the speed of C. It's impossible. And what Lazy Dynamics wants to also kind of prove that this idea of you can't have Bayesian reasoning and Bayesian inference and do it fast and for low power. We want to show that that's actually possible. And so we're going to actually build a pro version of ArcGIS to basically well, to help other companies build natural AI systems, right? I'm going to zoom out now, the last 2 slides. There is this hype cycle that just came out. I mean, it's every year. Gartner is a market analysis firm that plots how they think that interesting technologies will develop. Basically, they say interesting technologies or some technologies, nobody knows about them, then it gets hyped, but the hype doesn't pay off. People will see, well, there are some limitations, so then it overshoots in pessimism, and then there is this return of investment curve that saturates. There are 3 interesting points on this graph, I think. There is the traditional engineering disciplines here, computer vision. All the way on top, or just a little bit over the top, generative AI, and all the way in the left is first principles AI or natural AI. We are all the way on the left. And how does this compare to the other 2? Well, traditional engineering disciplines, control theory, signal processing, computer vision, that's basically from my time, from 20, 30 years ago when I studied, and still in universities, we have these different groups. I'm in the signal processing group. The floor above us is the control theory group. And for us to design systems, well, I have to study a couple of years, learn all the math of my field, and then I can design algorithms, right? It's very expertise driven. The great thing about generative AI is that in terms of investment, well, a lot of the expertise is replaced now by data, big data. And it's a lot easier to collect a big database for many applications than get complete experts in a field, right? So what natural AI will bring to the table is that rather than big data, we automate the reasoning. It's going to be completely automated, right? As a designer, you still have to write a probabilistic model, but it's half a page. You don't have to collect the data because these agents go out in the world and collect their own data. So this is, I think, going to be a step up on generative AI, where you still have this problem of collecting a big database and training on a big database. Finally, this is just an extract from a model of the brain. Somebody drew his model of the brain, and I took a small part of it. And what's interesting about this is, well, our brain is completely self-organized. Nobody wrote this, right? This is the result of evolution. We have about 10 million sensory inputs to our brain. We have 100 billion neurons, and we relay that processing to more than 50,000 muscle spindles, our actuators, right? It's a control system of size and complexity that we will never be able to engineer. Still, the brain doesn't know anything about all our traditional disciplines that we teach in university. The brain doesn't know Shannon's laws, at least not at cellular level, at the neuron level, right? Doesn't know about Bellman's recursive equations. It just does free energy minimization, nothing else. And so I think that in the long term, some of these disciplines are going to be replaced by natural AI. If you want to build really complex control systems, like ourselves, it's not going to be enough to study control theory or to study information theory. You have to build a model, go out in the world and do proper reasoning with the data. Proper reasoning means Bayesian reasoning, and you want to do it in real time, you want to do it fast, low power. That means you have to do Bayes or variational inference, And to realize that, you have to do it with message passing. That's the only way to make it ultimately affordable to do real-time proper reasoning. So, and that's where we want to go with natural AI, and we want to build or make RX Infer the toolbox to support this, this new field of AI, natural AI. Thank you very much.
Thanks, Bert. It was a great talk. Does anyone have a question? Yes, I have a first question.
Oh, can you hear me?
Yeah, sure.
I want to go back to the slide when you compare the kind of the expertise-driven design, then the big data design, and then now the kind of the natural reasoning part. Because I'm just wondering, like, how do you see like the role of the data and the role of the expertise, especially when reasoning is an expensive time given the context? So a very easy context I would like to give is, let's say if you're playing cricket or baseball, and there's only so much time that you can react when the ball comes to you. So in a very high performance environment, if somebody tells you a certain technique, certain expertise technique is going to be helpful, and then a data analyst is telling you what is the probability distribution of this particular pitch is going to give you, that is going to help me as an agent to minimize my free energy a lot. So how do you see all these three kind of things combined together, especially when reasoning is going to be slow, or convergence is going to be slow without the help of the other things?
Yeah, so it's a very good question. The answer is complex, right? In general, you can think of variational free energy minimization as reasoning, proper Bayesian reasoning, and for problems when you have very short time, it may not be enough. So you may not get the accuracy that you need. So then, well, basically you cannot solve the problem. But you can, of course, do what's called amortization. You can learn, learn, let's say, direct consequences of actions if they occur a lot, right? So in a way, and that will reduce the energy consumption. For instance, when you learn how to drive your car, in the beginning, all your predictions are off. Right, you turn your steering wheel, and it's not going to do what you want to do. So you generate a lot of prediction errors, and you need all your brain to process those and learn from it. You cannot even talk to your instructor. Once you know how to drive and your predictions are correct, so your generative model has become correct, I mean, you can drive home, you don't even know how you got home, right? I mean, it's completely almost unconscious. So over time, this approach leads to less and less energy consumption for the same accuracy, and that can be enhanced by amortization, where you actually learn direct mappings from, let's say, sensory inputs to the proper actions. Yes?
It's interesting you go for the driving instructor principle, but would you think that the expertise of driving instructor helps the convergence, or maybe actually leads to a stable convergence of your free energy principle? Or otherwise, in a random environment, if you don't have any guidance, you might converge into something that does not give you the best answer? Do you think that is
Well, it's hard. I mean, let's say we are all a local minima, right? None of us is a global minimum. We are all just minimizing our free energy with our computational budget. And our computational budget fluctuates. Because, well, if I walk downstairs here, I suddenly have to attend to my walking downstairs, and I have less energy for other things, right? So over time, whatever task you do, you have a completely fluctuating computational budget, and the brain is the brain is constantly busy to basically to control where goes my resources, right? It goes to where the highest priority is. There's no guarantee that you can resolve your task. There's no, I don't think it's the right approach here is to think of, well, do we get long-term convergence of this process? There's too many fluctuations in computational budget, in tasks to do, in interruptions. You do the best you can, and over time you get better because your predictions get better, your model gets better, you make fewer prediction errors, and that's why we, well, it's good enough to survive. right?
If you could maybe go back to the slide with the actual model of the guys working running around in the warehouse.
Summers in the Netherlands are fantastic, right?
I wanted to ask, in what sense does the model that you showed the code, in what sense does it encode the movement of the how the little stars, how the little arrows are running around? Because I'm
in the first line we code the movement, let's say the dynamics of the agent, and the other code is there to the constraints that the agent has to observe, but they are also encoded as probability distributions, so it becomes a large probabilistic model. The idea is this, that variational free energy minimization in a generative model is the only thing going on. If we would just try to predict how the world works, then we would build a model of the world and nothing else. Our brain would be a proper scientist. But we have biases. We don't want to run into collision. We don't want to have collisions. We have speed constraints. All these constraints makes the brain an engineer. It's not, our model of the world is biased. We predict that I predict that my temperature is going to be 36.5 degrees. And by variational free energy, all the possible processes are called upon to make that prediction come true, right? So we have a bias model. We predict sensory inputs that keep us alive, that are good for us, that are desired, and inference does everything else. But the actual dynamics here is very simple. The thing can only move, as a simple, almost like a random walk. Yeah.
What I meant in this. Oh, sorry. I meant in the sense that if, let's say, I wanted to add acceleration to this thing, like how would I go about it? How does this normal with mean and covariance encode the movement?
Well, acceleration is encoded. I mean, x here is a vector of position, velocity, if you will, acceleration, and so forth. So we can encode in this linear equation the differences or let's say a difference of velocity. So it becomes a matrix multiplication.
Hi, nice talk. So thanks, very interesting. In my sector, we tend to use like reinforcement learning for some of these problems that you seem to be solving. So I was wondering, could you comment a bit on like how they are different, where you would go with the one or the other, or I don't know how familiar you are.
Well, there are philosophical differences. I mean, in a way, variational free energy minimization, or the free energy principle, is sort of an umbrella over, I mean, you can see reinforcement learning is a special case, but there are philosophical differences and realization differences. The most important is that in reinforcement learning, in order to determine planning and actions, we actually, it's not a reactive system. You actually write an algorithm for clever tree search. Here, we say, no, there is only variational free energy minimization going on, nothing else. And this variational free energy minimization is implemented in small parts, distributed variational free energy minimization by passing messages. Each message or collision of message carves a little bit of free energy minimization away, and it's completely autonomous and distributed, which means we can also just say, I'm not going to do this one, I'm not going to do this one. And so in the end, we think this approach will lead to a much easier way of online to be able to cope with these power budgets that we have. We don't have this problem of, hey, I'm in the middle of a loop and I get interrupted. There is a continuous process of variational free energy minimization that can be interrupted at any time. So this approach is better for environments where things are not as predictable, where the environment can be very complex. I drive a car and suddenly I'm in a very busy traffic, or very easy traffic. that has a different computational footprint, and this system naturally deals with that. It seeks the most accurate model or prediction for the budget, and it does it in a very smooth way. So I think the way of implementing is a big difference.
Okay, thanks.
Sure.
Here is. Do you want to?
Others.
Hi there, thanks so much for the talk. Yeah, really, really interesting topics. So I wanted to ask, with generative AI, which you seem to be making the comparison with throughout the talk, it's got this ability to generalize from data. So you feed it data, ChatGPT has a lot of data, it can make generalizations based on the data. From what I understand, and that might not be much, this seems to make generalizations based on the model, and someone has to program the model. So does this mean that you're kind of putting the responsibility of an AI system in the hands of a developer? Like, for example, you had a drone example. If I'm deploying a drone in a military situation, for example, is that drone being based on a model created by some programmer behind the drone?
Yeah. I mean, the Bayesian inference in general is pretty good at generalization, because it will not overemphasize on accuracy, which will be overfitting the complexity term. If I only do complexity, I do underfitting, and so it finds a good balance that in general. But indeed, you have to program a model currently and say, well, these are the constraints, and you can do you get data from the environment, you minimize free energy, but you must obey the rules of your model. Now, in biology, our model changes over time as well, under pressure of free energy minimization. Natural selection is free energy minimization over a very long period of time. So we also are interested in working on structural adaptation under the pressure of free energy minimization and adapt the model over time. Because, yeah, if the world changes, you might actually need a new model, but yeah, everything at a time, right? So currently not working yet. Yes.
Is it possible for these agents to memorize the wall locations? And if so, where is that information stored?
Yeah, so I mean, they have in the constraints. We basically encode the wall, but I mean, what we do is we give these these agents sensors, and we say, well, if you get close to an object, you're going to feel that object, and then there is this constraint built in. You want to avoid collisions, so then logical reasoning means I'm going to go the other way. That's how it works. So we just assume this is a simulation that it sees the wall when it gets close to the wall.
Okay, so that sounds like bug pathing then. Like, is it, let's say as a programmer, I want to deploy these robots to a warehouse, and I don't know the warehouse floor plan, I don't want to deal with that, but I know that the pillars in the warehouse are going to stay in the same place, and these robots are going to be there for years. Is it possible for me to write 15 lines of code that then has the robots themselves will end up figuring out and remembering where the walls are, kind of like a Roomba would?
Yeah, in principle, yes. I mean, free energy minimization goes over not just over states, but also over parameters of the model. So in principle, you can just learn the model over time, and then it becomes hard-coded in the model, and so it would know this, right? Absolutely. There's nothing that would, and that would currently work. In our Infer, we can do, let's say, state estimation, parameter estimation, just not yet the structural adaptation of models.
We have room for one more question there.
Yes, I have a follow-up question on that. So these robots, will they actually get better at warehouse work as time evolves? And is that state saved somehow so that they will do better also in a new warehouse?
I'm sorry, can you quickly repeat the question? I didn't see where the sound was coming from.
Sorry. Yeah, so the question is if these robots will get better over time. For example, bring the package more quickly, and if they will also be better than an untrained robot when they enter a new warehouse.
Yes, yes. I mean, if your hardest constraints are bring the package, and you make everything adaptive, that it will get better and better over time. First at smaller timescales, just Kalman filtering. It will do Kalman filtering, although it's not aware it's doing Kalman filtering. Then parameter estimation, and then hopefully at some point structural adaptation. It's the same thing as like throwing water off a mountain, and it just, with all the rocks and whatever, it just goes zigzagging its way down. And if you come back 10,000 years later, is going straight down, because it will remove the obstacles if it has just one task. So if you just say you have one task, bring the package and no collisions, and everything else is adaptable, then yeah, it will learn the parameters and hopefully at some point learn the proper model. Yeah, yeah.
Thanks, Bert.
Sure.
It's a great talk, great discussion. Extra round of applause.